Hello everyone, my name is Brodi D Elwood, and I'm a graduate student at Harvard University, working with Professor John Kovac in the BICEP Keck Collaboration, and today I'm going to briefly talk about calibration efforts for the BICEP Keck CMB polarimeters at the South Pole. So, what do the BICEP Keck telescopes actually do? Taking a step back, the Big Bang happens, and it's believed that immediately after a period of inflation occurs, a period of rapid spatial expansion. This rapid expansion produces primordial gravitational waves, which interacts with the hot, dense universe to imprint a particular polarization pattern in the relic light we see in the early universe. We measure this relic light from the Big Bang through our telescopes in order to build a deep polarization map in search of primordial beam modes that can be reduced to a cosmological parameter R, the tensor to the scalar ratio, which is just a measure of how strong inflation was in the early universe. So what problems do we face when we try to measure R, or the tensor to the scalar ratio? Well, I think we have at least two big problems. First, the polarization signal is extremely faint. It's on the nanokelvin scale, extremely cold. Also, we have to look at the CMB through radio telescopes, and telescopes, like any instrument, cannot see perfectly. We have to understand the characteristics of our instrument to draw any meaningful conclusions from it. In order to pull the real signal out, we must precisely understand the instrumental effects, such as the telescope angular response, which I'll talk about later. Other things to consider are the fact that we only observe part of the sky. Our scan strategy also enters into our ability to make polarization measurements, accurately calibrating instrument gain. In other words, going from feedback units in volts to Kelvin CMB is especially important when using external maps for analysis like we do with Planck. And also we also deal with external interference from terrestrial and other sources, which has been a problem for us in the past. As I mentioned earlier, one area that requires much characterization and calibration is a telescope's angular response, or beam. For those of you familiar with optical telescopes, this is called the point spread function. In other words, this is how the telescope actually sees. And ideally, for the BICEP Keck telescopes, the beam would be Gaussian. In other words, as you move radially outward, the beam response of the telescope should drop off as a Gaussian curve would. How do we go about actually measuring these beams? Well, we stick a mirror immediately above our telescopes so that they can see over their ground shield at a chop source, which chops between ambient temperature and the sky. And we scan across this chop source, and this gives us a signal which ends up being our beam that we want to measure. So why do we go through all this trouble to measure beams? Well, let me take a step back and discuss what is a polarimeter. In particular, because we are a polarimeter, the BICEP Keck telescopes are polarimeters that measure polarization by differencing the signal from two co-located or orthogonally polarized detectors, which we call A and B. Any difference in the beam leaks a false temperature signal into the polarization signal. In other words, if the orthogonal polarizations effectively see differently, this will show up as a false polarization signal, which is a big deal, a big problem. Now, what does this actually look like? We can take the difference between our A and B beams, which tells us how much they see differently. Ideally, there'd be no difference between A and B, but with real measured beams, we can find common patterns or modes in these difference beams, which are seen here to the right. Since these beams should be fairly constant in time, we can quantify how much of each mode is in each beam and correct for the effect of difference beams. And what else are beams good for? Well, in order to compare it to external maps taken by other radio telescopes, we need to count for our own telescope's beam. This is particularly important when doing absolute gain calibration, where we calibrate for instrument measured units in volts to Kelvin CMB. So what work is there left for an enterprising young graduate student to do? Well, as I mentioned before, we can deconstruct our beams into certain patterns, and once we correct for those patterns, what we get left over is what we call the residual beam. We want to understand what's going on with the residual beam and also correct for those effects in the residual beam. We also want to observe this telescope ground environment to understand what's going on around the telescope even more. We want to optimize the number of beams taken given our mirror constraints. Our mirror is only so big. And also in future experiments like CMB stage 4, we want to implement new beam mapping strategies to record amplitude and phase information.